Hi, Assalamualaikum warahmatullahi wabarakatuh. Today I would like to talk about the idea of orthogonal projection. And here we have a vector space. So let's say here is an example of having a vector space with 2 dimensions. So in this vector space, we might have vector v, and then you would like to project this vector into vector u. So there is another vector here, so you want to project vector v onto this non-zero vector u. And the formula to find the projection of v onto u is given by this one. So you can see here, this is the vector that you would like to project, and the rest here are the projection of that onto non-zero vector of u. Graphically speaking, well, you can imagine having, for example, this vector here. So maybe this is the position of vector v, and you can think of it looking like that. And now you want to project this vector perhaps onto this specific, for example, if you have a plane here, so maybe the projection of vector v is going to be somewhat along this line. Okay, so this is what can we say, the projection of vector v onto u. Okay, so this is the thing. Also, when you have this vector here, the new vector, we can think of it as a new vector, there will be another vector, so we call it perpendicular. So this vector here will be perpendicular with respect to this this blue vector here. So perpendicular means well, you're going to have 90 degrees, and we're going to label that with perpendicular of vector v projected onto u. And therefore, what we can say is there is a relationship between all the three vectors here. So this is vector v, this is another vector, which is the projection of vector v onto u, and this is another vector. So the relationship between these two vectors are given by this one here. So v here is the combination of projection of vector v onto u and the perpendicular of vector v onto u. So that's a simple idea of orthogonal projection. Now, let's say we have a slightly complicated idea. Okay, so we have W is a subspace of a vector space here, and we have a set of vectors. So we have vectors u1, u2, and everything here. This is a particular set which is an orthogonal basis for W. And if you have any vector in this vector space, the orthogonal projection of v onto W is defined in this way. So you can see that this is the basic idea of what is orthogonal projection. You want to project v onto something else. So in this case, projection of v onto W. So this is the basic idea which is already given here. You want to project v onto non-zero vector u, so we have one vector. But in this case, we have a lot, u1, u2, and uk. So the idea here is you do it one by one. So here with respect to u1, projection of v with respect to u1. And then you do it for the second time, projection of v with respect to u2, because here we have the second vector here, and you do it until the end. So projection of v with respect to uk. So u1, u2, and uk all is related to this subspace W. And once you are able to get that, you will see that this relationship comes directly from this idea. From this idea. Well, if v is equal to projection of vector v with respect to u plus perpendicular of v with respect to u, we can find what is this vector perpendicular of u with respect to v, and this is equal to vector v minus the projection of vector v with respect or onto u. Okay, so this is what is given here. So the name of this is component of v orthogonal to w. Perhaps we can try and visualize what the process is all about. So here we have a vector space. So this is the vector space. And imagine we have a subspace, which is sort of a subset here. So this is the subspace. And we call this subspace W. Okay. And let's say we can find, or we are able to find the orthogonal basis. So here is orthogonal basis of W, and it is described using this notation here, which is a set of vectors named u1, u2 until uk. So this is orthogonal basis of W. Now imagine that somewhere here there is a vector. So in this vector space there is a vector. So v here is a vector. How can you project v onto W? How can this v here be projected onto W? So project to W. So in order to do this projection, what you need to consider is you need to consider the formula here, which relates the orthogonal basis of W, and so it is given by this formula. Okay, so I'm just going to write down. So the formula here is just, well, we're going to project it one by one. First, with respect to u1, so here we have u1 dot v, everything else is u1 times with u1, and then you're going to do that for each vectors here until the last one. So the last one will be, well, uk with vector v, so uk and uk. So I hope you can notice that the projection of vector v, this is what we are looking for, and so it appears here, okay, and the rest is, you know, straight away from the orthogonal basis. For example, u1, and u1 direct from this vector in orthogonal basis, and similarly uk comes from this vectors orthogonal basis of W. Okay, so that's the idea, and the whole thing here has a name. Okay, the result here has a name, and it is called projection of this vector into the subspace W. Okay, and once you are able to get that, from here you will also be able to get what is perpendicular of vector v with onto this subspace of W. And to know this answer, it is easy. You're just going to take this vector minus the projection. Okay, so vector minus vector V minus the projection of vector V onto the subspace W. So these are the two results that you might want to pay a bit of attention, this one and this one. So here is a special name to it. It is the component. So here is the component of vector V that is orthogonal to W. Okay, right, now without further ado, let us try and do some examples. Okay, so here is W, which is a subspace. So this is the subspace on this vector space with 3 dimension. This is vector V, and here we have orthogonal basis. So this is the basis of W, and the question is asking you to find the orthogonal projection of V onto W. So in order to project V onto W, we are going to use this orthogonal basis for W. Okay, so that is what we need. That's the information that we need. Well, right now, here is, well, I'm just going to call this orthogonal basis. I'm just going to call it a simple name. So I'm going to call this as set of U, and here consists of U1 and U2. And this is the same thing as having this representation. Okay. Alright, so this is the basis. So I'm just going to write the little note here, orthogonal basis. Okay. Now, notice that this vector here, for example, has to fulfill the idea of, or the definition of W. So W here is a vector with x, y, z, such that when you do this operation, x minus y plus 2z, the result is 0. So you can sort of see that here is x, y, and z. So if you have x minus y plus 2z, this is equal to 1 minus 1 plus 2 times 0. So 1 minus 1 plus 2 times 0 is going to be equal to 0. So it has to fulfill the condition set or defined here, okay, in this part. So similarly for this one here, you can see x is negative 1. So minus y is 1 plus 2 times 1. So negative 2 plus 2 is also 0. So again, this vector here, it fulfills the condition given in this part for W, which is the subspace. Okay. Well, that's just the side story. This is not exactly related to what we're going to do. I'm just explaining the meaning of this here, what it means really, this part. Okay. So, well, to find the orthogonal projection, again, the formula is, so I'm just going to call this the projection of vector V onto W, and because W is the subspace and we have this orthogonal basis, we're going to do it one by one. So first we are going to have the projection of V onto this vector here. So you will have U1 times V. The rest will be U1, U1, and U1. Plus the projection of V onto this another vector, which is U2. So we have U2, V, u2 and u2, and here is also u2. So it is quite easy once you get the hang of it, the formula. So based on this, okay, I might need some space, so I'm just going to use this space here. Okay, let me just use this space. Okay, so what I need is I need to calculate what is u1 times dot product with v. So that would be u1 is this one, so 1 1 0. V is this guy, 3 negative 1 2. So if you multiply them, so that will be first component with first component, so 3 plus this and this, negative 1 plus 0, so this is 2. Okay, next is, well, this part. So here I have u1 dot product with itself, so 1 1 0 1 1 0, so this will be 1 plus 1, which is equals to 2. Okay, just going to substitute the values here, so it will be 2 over 2 for this part. And what is vector u1? Vector u1 is 1 1 0. Okay, now plus. Okay, now we're going to do this part. Okay, let me just erase this. Okay, so now we're going to start off with finding what is u2, the dot product of u2 and v. So u2 and v is, this is u2, negative 1 1 1, and v is this guy, 3 negative 1 2. So the result is going to be negative 3 minus 1 plus 2. So this is negative 2. Okay, and then this part here, the denominator, this is u2 dot product of u2 and itself. So u2 is this one, negative 1 1 1, negative 1 1 1. So it will be 1 plus 1 plus 1 when you multiply, or when you add the multiplication of each component. Yeah, so we have 3. Therefore here we're just going to substitute the values, negative 2 over 3, and vector u2 is negative 1 1 1. And if you simplify the result, okay, so we're going to simplify the result of this. Oops. So if you simplify that, it will be, this is equal to 2 over 2 is 1, so 1 multiply with this vector, you will get the vector back, 1 1 0, plus here is negative 2 over 3, so this is 2 over 3, negative 2 over 3, and this is also negative 2 over 3. And if you add them up, so 1 plus 2 over 3, 3 over 3 plus 2 over 3 is 5 over 3 for this one, the first component. 1 minus 2 over 3, which is 1 over 3 for this one. And then 0 minus 2 over 3, so negative 2 over 3. And this is the orthogonal projection of V onto W. Okay, so this is the answer for question I. And the next question is asking you to find the result or the component of V orthogonal to W, and this is just denoted by perpendicular of V This is onto W, okay? And to find this, what we need to do is we just need to have vector V minus this result here. So vector V minus this one, okay, projection of V onto W. So we have here 3, negative 1, 2, minus the result that we have. This is 5 over 3, 1 over 3, and negative 2 over 3. So 9 minus 5, this is 4 over 3, negative 3, negative 1, so negative 4 over 3. This will be 6, will be 6 over 3, plus 2 over 3, so this will be 8 over 3. And this is the answer for question 2. Okay, I think that's all for now. Thank you very much for watching, and I'll see you in the next video where I'm going to talk about the Gram-Schmidt process. And you will see that in order to do this, you need to be comfortable with the idea of orthogonal projection. Okay, so I'll see you there. Thank you again for watching.